How did a machine designed to protect its crew become a massive 45-ton trap? The reason lies within pre-war blueprints. The Battle of Kursk in 1943 would reveal the grim cost of this engineering failure. Crews entered combat believing they were fully protected inside a thick steel hull. But the final 45-ton mass matched the Soviet IS-2 heavy tank exactly. The sheer weight of the vehicle doomed the design before it ever reached the front lines. Before the conflict began, German designers initiated the VK-20 series as a light 20-ton concept. Engineers carefully calculated the required technical specifications. They designed the mechanical systems and running gear to handle a strict maximum of 24 tons. It was a rational plan for a medium tank operating on standard European terrain. However, demands for thicker steel plates and larger guns steadily drove the mass upward. The underlying foundational structure never received the necessary physical upgrades. The crew's illusion of safety evaporated the moment the driver engaged the heavy engine. Overloaded transmissions emitted a loud metallic screech during every minor turn. The suspension visibly sagged under the unnatural weight. It generated the distinct sound of deforming metal across steel nodes created for much lighter loads. Mechanics worked constantly beneath the massive chassis, physically exhausted from replacing shattered drive components in the mud. Despite nearly doubling the initial vehicle mass, the calculated structural load limit on the running gear remained exactly 24 tons. An armor-piercing shell strikes sloped steel. It deflects into the sky. Artillerymen panic and abandon their defensive guns. Pre-war infantry illusions shattered against T-34 armor during the dusty summer of 1941. Technological despair quickly consumed the entire front line. German motorized forces initially decimated light Soviet BT tanks. Then the combat reality changed. Invading troops encountered the heavy T-34 and KV-1 chassis. Standard anti-tank armament proved completely useless. The sharp, high-pitched ringing of 37mm shells bouncing harmlessly off angled plates haunted defensive gun crews. Desperate ground formations faced impenetrable metal structures. High military command dispatched a specialized technical commission. They traveled directly east. Engineers rigorously evaluated captured enemy designs. The commission forcefully demanded the immediate development of a high-velocity cannon and thickened armor to replace the Panzer IV. Why did a sophisticated transmission become a curse for the crews? The drive shaft ran directly beneath the combat compartment. Increasing design complexity punished frontline mechanics and reduced total vehicle output. Engineers mounted the petrol engine in the rear, yet positioned the drive sprockets at the front. This mandated a heavy steel drive shaft spanning the vehicle's entire length. Inside the enclosed space, 5 men operated the 75mm gun. A constant smell of raw petrol leaked into the tight combat compartment from the rear engine bulkhead. When the transmission failed, the extraction process became an operational nightmare. Maintenance crews knelt in thick mud, struggling to dismantle the heavy gearbox and access the drive shaft hidden beneath the armored floor. Manufacturing these interlocking hull structures consumed critical factory hours. Producing 5 complex Panthers cost the Army 6 reliable Panzer IVs. This manufacturing trade-off created severe logistical gaps across the Eastern Theater. Such a deficit meant that entire panzer divisions remained without heavy armor support during critical defensive battles. The ultimate production shortfall amounted to exactly 1,000 armored units. 2 machines. They burned directly on the railway platforms before the offloading sequence even began. The absence of proper testing time transformed the first armored units into dead men. Before reaching the front line in July 1943, multiple tanks ignited spontaneously during routine transit. The entire development cycle took less than 1 year. Engineers bypassed standard technical trials due to strict production deadlines. The battlefield replaced the test range for the complex Maybach power plant. This V12 engine produced 650 horsepower, but the design defect resided deep within its exhaust system. Incorrect fuel mixtures prevented complete combustion inside the cylinders. Unburned gasoline leaked directly into the hot exhaust manifolds. It detonated. The resulting engine fires rapidly breached the rear steel bulkhead. Thick smoke from raw fuel instantly filled the combat compartment through unsealed gaps. Oxygen vanished. 5 crewmen sat trapped inside a confined fighting space. The enclosed interior contained 79 main gun shells and highly flammable hydraulic fluids. Exiting the burning vehicle required manually unlatching heavy steel hatches. Men choked on toxic fumes before the flames even reached the primary propellant charges. The internal temperature of a burning tank exceeds 1,000 degrees Celsius in seconds. Crews burned alive without absorbing a single enemy armor-piercing shell. The technical rawness of the vehicle executed its own operators. 200 Panther D models rolled straight into active combat operations. Exactly 200 crews deployed to the Battle of Kursk, confined within 45-ton fire traps. Where did 130 abandoned machines come from within 48 hours? This operational failure stemmed directly from accelerated deployment and the severe panic of completely untrained drivers. A massive combat vehicle plunges blindly into a flooded anti-tank trench. Here, the gurgling sound of a drowning engine immediately signals a catastrophic navigational error. Years later, this armored platform would become a steel tomb for thousands. But in July 1943, the initial 200 Panther D variants simply drove into deep mud. This specific deployment constituted the most extensive combat debut of a German tank design at that historical juncture. Overwhelmed crews attempted to force manual crossings through prepared minefields, permanently bogging down entire motorized companies before their main weapons could discharge a single round. The numerical data surrounding this chaotic offensive reveals the profound structural inadequacy of their hasty introduction. 130 out of 200 deployed machines suffered critical mechanical breakdowns, completely failing without absorbing a single enemy impact. 18 units were definitively lost on the first operational day, followed by another 37 terminal losses on the subsequent morning. Panther crews managed a minor tactical success when they eliminated 6 American-manufactured M3 Lee tanks. However, internal communication failures proved far more lethal than Soviet fortifications across the active battlefield. A Panzer IV gunner identified an unfamiliar chassis silhouette through his optics and instinctively initiated a main gun firing sequence. The resulting friendly fire incident instantly detonated the new Allied machine, guaranteeing the total annihilation of its trapped crew. The crew of this shattered machine never learned its dimensions. Security protected blueprints. Simultaneously, this secrecy denied German tankmen combat survival. Instructors enforced total information blackout. Trainees faced punishment for writing notes. Photos meant prison. Men memorized complex hydraulic schemes. Standard Panzertruppenschule training courses took 12 weeks. They got hours. Memory replaced technical manuals. Crews died fast. By late 1943, combat data arrived. Gunners eliminated 500 Soviet T-34 tanks. They lost 100 Panthers. Paper showed victory. Reality showed mechanical collapse. Internal breakdowns crippled units faster than incoming Soviet artillery shells. Factories pushed out upgrades. Model G variants arrived. They constituted half of total Panther production. But core physics remained broken. Drivers felt the physical overload. 45 tons of steel pressed downward. Torsion bars snapped. Transmissions failed constantly. Despite all later armor modifications and turret redesigns attempting to save the flawed vehicle, engineers could not alter the reality that this massive structure sat upon a suspension originally built for 25. How did Soviet infantry penetrate a heavily armored machine using only hand weapons? They fired 14.5mm rounds through a narrow gap between the sponsons and tracks. The chassis collapsed continuously under 45 tons because engineers concentrated nearly all that mass into a single forward steel plate. 80mm of rolled homogeneous steel positioned at a 55-degree angle provided an effective line of sight thickness of 139mm. This geometric configuration granted the crew a level of frontal protection roughly equivalent to the vertical 100mm plate of the heavier Tiger I. Moving away from this reinforced front, the side hull plating dropped dramatically to 40mm. While the frontal glacis remained essentially impenetrable, the rear engine deck consisted of just 16mm of flat metal. Artillery bursts detonated overhead. Fragments showered through this thin horizontal barrier, bypassing the massive frontal protection. The rounded gun mantlet created an even more lethal geometric trap for the men sitting directly underneath. An incoming kinetic projectile would strike the curved outer shield, lose its horizontal momentum, and deflect sharply downward. The thin roof shattered instantly. The deflected shell smashed vertically through the 17mm hull roof, showering the trap driver and radio operator with high-velocity spall. Below the main hull line, the dull thud of Soviet rifles echoed as 14.5mm bullets punched through the lower sponsons. German engineers hastily deployed thin steel side skirts as a temporary measure to tumble incoming projectiles before they struck the lower hull. They eventually redesigned the turret mantlet, adding a flat metal chin to redirect hostile kinetic fire away from the forward compartment. Planners subsequently drafted extensive blueprints for a standardized replacement design, sharing interchangeable drivetrain components with the heavier Tiger II. Only one hull was finished. Factory workers sent this single completed Panther II chassis directly to a scrapyard. Soviet commanders launched dawn assaults. They know the mechanical truth. German mechanics cannot move tanks. Night frost freezes the tracks. Ice locks the overlapping wheels. Tanks remain paralyzed until noon. While engineers draft turret shapes, crews freeze. Men hold heavy steel crowbars. They smash solid frozen mud. Brutal physical labor breaks human bodies. The complex suspension absorbs impacts. It handles half a meter. Cross-country mobility remains unmatched. Yet daily maintenance ruins morale. Crews face total physical exhaustion. The final drive shatters easily. Gears strip under massive torque. Engineers promise 1,000 kilometers. That represents the engine limit. But complex transmissions fail much faster. Distance kills tanks. Strategic mobility simply vanishes entirely. The distance from Berlin to Leipzig breaks the delicate gear teeth. A vast eastern front requires constant movement. This heavy machine cannot travel far. Records from May 1944. They show slight mechanical improvements. Lifespans reach 2,000 kilometers. But war consumes industrial resources. Production quality soon plummets downward. Severe material shortages plague late production models. Alloys become dangerously brittle. Final drives fracture during transit. Machines die. Metal fails. Steel cracks under immense weight. Tanks sit dead. Crews walk away. A fatal compromise destroys everything. For a heavy machine built to conquer the vast Russian steppes, the ultimate lifespan of its transmission was exactly 150 kilometers. How to justify endless mechanical agony? By mounting the 75mm KWK-42L70 gun. 50 high-explosive and armor-piercing shells sat packed together in a single thin side sponson. The barrel exceeded 5 meters in length. Inside the fighting compartment, space was critically tight. The crew practically sat on a powder keg. An armor-piercing capped round left the muzzle at 935 meters per second. At a range of 1 kilometer, it punched through 112 millimeters of steel. With a scarce tungsten round, velocity hit 1,130 meters per second. Penetration reached 150 millimeters. This meant a Panther could pierce the 152mm frontal plate of a British Churchill Mark VII tank almost point blank. By late 1944, technology advanced into the dark. The Panther became the first tank equipped with active infrared gear. The FG-1250 system paired a spotlight with a specialized scope wired directly to the gunner. He peered through the eyepiece. A greenish silhouette of an enemy target materialized in the pitch black. An invisible infrared beam cut through the night. The Americans still relied on blinding white searchlights that exposed their positions immediately. Western allies possessed detectors capable of picking up infrared emissions, forcing German crews to strip the kits before combat in the West. Only the Eastern Front saw these optics in action. Advanced ballistics and optics coexisted with a fatal flaw. The main armament allowed engagement from well over 1 kilometer away. But if the enemy fired back and hit that vulnerable side sponson, 50 stored shells detonated simultaneously. The tank became an incinerator. The gunner worked the breech. The loader shoved rounds into the chamber. Maximum rounds per minute reached exactly 6. But perfect ballistics meant absolutely nothing. The gunner lacked basic practice. He never fired a live shell. An untrained driver yanked steering levers. He shifted the gears blindly. Gears ground. The transmission screamed. He overstressed the heavy engine immediately. The final drive shattered inside. Engines died. The tank stopped. Poorly trained operators caused massive failures. They mishandled complex gearboxes daily. Drivers lacked proper driving courses. Training vanished. 400 tanks deployed to Normandy. It was summer 1944. This required 2,000 qualified men. Germany lacked this specific human resource. Drafted teenagers manned the vehicles. They learned operations under actual fire. The French bocage landscape restricted movement. Thick, tall hedges blocked the tracks. The 75mm barrel hit dirt walls. It struggled to swing around tight corners. Close terrain allowed dangerous flanking maneuvers. Allied forces closed the distance quickly. They fired from very short ranges. British Sherman Firefly tanks waited nearby. They carried heavy 17-pounder guns. These weapons pierced thick frontal armor. Heavy losses mounted on both sides. Survival required basic human reflexes. The outcome of every single sudden duel among the narrow green hedges was simply decided by whoever pressed the steel trigger first. Why weld fake sheet metal onto heavy armor? For a single illusion of camouflage. In the Ardennes, crew desperation peaked. 5 Panther tanks attempted to pass as American M10 tank destroyers. German mechanics welded false metal plates across the angled holes. These modifications altered the original turret silhouette. Fresh American olive drab paint covered the rough German Zimmerit anti-magnetic coating. The strong smell of fresh paint mixed with the freezing December mud. The disguise failed immediately. American troops quickly identified the mismatched proportions and the distinct sound of the Maybach engines. All 5 tanks burned. The war ended. From 1946 to 1950, the French army incorporated roughly 50 captured units into their armored regiments. French crews praised the lethal 75mm gun ballistics. The optical sights remained superior. Yet, the core mechanical diagnosis stood unchanged. The powerful main armament never compensated for the fatal drivetrain design. The 45-ton weight constantly sheared the overloaded final drives. Without a steady supply of specialized German spare parts, the heavy vehicles ground to a halt. Routine marches became disasters. By 1950, the French military officially abandoned the entire trophy fleet. The French army simply discarded the remaining inventory due to the exact same transmission failures that had plagued the original German crews.